Hey everybody, any big plans for the holiday? Y'all know we don't have school on Monday next week. So we'll come back live on Tuesday and then class on Wednesday. Yeah? Gotta get the new schedule. It was Monday. They're changing the taxes. Alright, but I'll see y'all back on Thursday. The Thursday lab, you are having lab on Thursday. I know she's told you so, but I just want to remind you. I know some labs are canceling, but I don't know why, but you are having lab on Thursday. Okay? It means you'll get done. Any big plans for the weekend? We're going to Mississippi? Not bad. Any other big events? The parade? Yeah. Huh? What's that? We're going to
Mississippi?
No.
Oh, we're going to Mississippi.
Where?
Little Black Tube. Or something. I don't know. I'm going to find it.
Okay, yeah, we're going Tunica Hills, I think. All right, folks, so let's look at Junction Rule. This is the last thing that'll be on your exam, which is on a week from Monday. 1 week from Monday is your exam, and this will be the last thing. It'll cover all of Chapter 4. So we got capacitors in Chapter 2, Chapter 3, which is, short, power, resistance, Ohm's law, and then Chapter 4, which is resistors in series and parallel. You got a little voltmeter, ammeter in there, and then multi-loop circuits, which is what we started last time. We'll finish them up today. They're a little bit different, but they're also similar to what we've been doing. So let me just sort of remind you of these rules. We've seen these rules before, but we're just sort of framing them a little bit differently. The junction rule says, we use this for parallel circuits, right? The circuit coming into a junction equals the current going out of a junction. And then the loop rule, which we had for resistors in series and capacitors in series, it says that these voltages have to add up to equal this voltage. But then we introduced the idea of plus and positive and negative voltages. This has a positive voltage. Remember the electrons, they come up and it's like the roller coaster, the chain that pulls you up, gives them lots of potential energy, and then they release that potential energy through the circuit. So these then have drops in potential, or negative change in potential. And so we write the loop rule now as 12 minus 8 minus 4. Now I want to introduce a couple more little nuances to the loop rule. When we apply the loop rule, it's going to be a little funky at first, and then you'll say, oh, now I get it. But when you apply the loop rule, you have to consider two directions. You consider the direction that the current is flowing, and you pick a direction to go around the circuit. And when you do that, we'll do an example next, but when you do that, let's say that one of my directions, the direction that you're traveling through the circuit, through which you're going through the elements. We're going, say, from A to B. And for this first one, let's imagine that the current is to the right. So here we'll imagine that my current is from left to right. And I'm traveling in this direction, going from point A to point B. In this case, your resistor acts like resistors act. That is, that they cause a change in potential that is negative. My change in potential is negative IR. However, let's still assume that I'm moving from points A to B, but now my current is not left to right, but right to left. In this case, going against the current, the resistor acts like resistors aren't supposed to act, and that is that you see a positive change in potential, plus IR. Now that doesn't actually happen in resistors. Like you don't actually get an increase in potential going across resistors, but it's just sort of a convention that we'll take that will allow us to use the loop rule. Okay, so this isn't physical, this is just something that we're going to use. You follow me? You always get a drop in potential across resistors, but we're going to take this and say that when you go against the current, which you don't usually do, your change in potential is positive. With batteries, you're not worried about the current, you're only worried about what your distance or what direction you're traveling. So if I'm traveling from A to B, this change in potential is equal to negative E. All right. So I like to think of my electrons. They're up here, whee, and then they go, woo, they slide down. And they lose energy when they're going from the big side to the little side. Do you see the slide on the battery? It's like right here. You'll see the slide? You'll see it now? The electrons lose energy as they go down that slide. Just like a kid going down a slide loses energy, gravitational energy. Okay? So my mom, she used to keep kids. Can I tell you a gross story real quick? Short. My mom, she ran childcare out of her home for a number of years. And she took a kid to the park, went down the slide. You know, they didn't wear shoes or anything, right? And it was one of those metal slides with the things that come over. What happened? Lost her what? Her toe, her little toe. Got caught in the side of the sled, took that thing off. I'm serious. Yeah. But the electrons, that doesn't happen to the electrons. The electrons just go, they don't have toes.
They lose one of their
I'm sorry, what?
They lose one of their quartz on their
They don't lose their quartz. Okay, and this is sort of like the opposite way. You don't usually go in a battery from high to low potential. Your electrons don't usually lose energy. Now, if I'm going in this direction, from little to big, it's like the chain going up on the roller coaster, right? And in this case, my change in potential is positive. So you'll need to know those sign notations. That will be very, very important. You're going to have probably 4 questions that will depend upon you knowing those sign notations. All right? I mean, you don't just have to know the sign, but if you get them wrong, you'll get the answer wrong. So for resistors, when you're traveling with the current, the change in potential is negative. That's sort of the normal way resistors do. They lose energy. And if you travel against the current, the change in potential is positive. You with me? Yeah. I'm going to show you. All right, we're going to do some examples. For batteries, when you have electrons traveling from high to low potential, that's like when I'm traveling in this direction, high to low potential, whee, right? The change in potential is negative. Delta V is negative E. The electrons have lost energy. And when you have electrons traveling from low to high potential, that's like sort of the normal way that we do batteries. The electrons come along here, and then they gain energy, allowing them to move out into the rest of the circuit. The change in potential here is positive. That is, delta V is positive of the EMF, the electromotive force. The electrons have gained energy. Now, unlike with resistors, the whole thing with V equal positive IR, that's not physical. That's just a notation that we take, a convention to make the rules work out right. But with batteries, there is a place actually where we have delta V is equal to negative of E, where we actually have a negative change in potential. Can you think of a time when you would want to run electricity, electrons, from the high potential to the low potential so that the electrons would actually lose energy going across the battery? Why would you want your electrons to lose energy going across the battery? Why? Huh? No, but you're on the right track. I mean, think about your devices. What do you do with your devices? You recharge them. And when you recharge them, that's what you're doing. You're running those electrons backwards. I mean, it has to be a special battery, right? You can't just do this with any battery. But you run those electrons backwards, and they actually deposit their energy into the battery. And it's a chemical process, but they deposit their energy into the battery. So this would be like charging a battery. Well, let's try this quick test. You're going to use the loop rule. Now, what you want to do is pick a direction for the current. It doesn't matter what direction that you pick. In fact, I'm going to go ahead and pick a direction for you just because sometimes students have trouble deciding. I'm going to say that the current is flowing in this direction. And now you want to start at some point in the circuit, say right here, and either go this direction or go this direction, and apply the loop rule as you go through. And applying those sign notations, okay? So apply the loop rule as you go through, and then solve for the current. You have some current I. Go through this circuit, applying the loop rule, the sum of the potentials is equal to 0. And then solve for the current. Feel free to ask your neighbor what they put or what they're doing. All right, let's stop at 220, 225, well, there were 225. Just guess if you're not sure. It's 5 more seconds. All right. And I think A is right. Let me show you. Don't worry, you're going to get the hang of this, okay? Once you see it a few times, people start to get the hang of it. I've picked the direction for the current. It doesn't matter what direction you pick. Or you can pick any direction you want. And now I'm going to pick a direction to go through the circuit. Doesn't matter what direction you go. You just pick one, okay? I'm going to go through this way. I'm going to start right there. I'm going to go through. I'm going to ask myself at each element, is this a positive or a negative change in potential? The 18 volts, that should be positive or negative? Right, because I'm going up the slide. It's like the chain pulling me up on the roller coaster. Here, I'm going through the resistor against the current, so that's going to be what? Positive. When I go against the current with resistors, the resistors do what they're not supposed to do. They have a positive change in potential. All right, so 18 plus 2I, that's my resistance times my current. Here, my electrons actually lose energy, so I got minus 12 volts. And then I have plus 1I plus 6.6I. And that's all equal to 0. So I get 6, 2, 3, plus 9.6I equals to 0. And solving that for I get 0.63. Now this isn't a multi-loop circuit. We're going to apply this to multi-loop circuits, but this is a single loop circuit where we can apply the loop rule. You can still see a question like this on the test, but we more want to apply this to multi-loop circuits. The loop rule is really nice. Just a second, Rachel. The loop rule is really nice because if you have a big complicated circuit, you can just pick out one little loop and say the sum of the potentials around that loop is equal to 0. All right, Rachel, I'm sorry. The 9.6 I got from, I said 2I plus 1I is 3I, and then plus 6.6I is 9.6I. I added these common terms here, here, and here. Okay? Thank you for asking that. All right, let's do an example. And you have a homework example, but let me tell you, in the homework, there's a multi-loop circuit, and it's important for you to work it. But don't get bogged down in the algebra, because setting up the equations is really important. But in your homework problem, the multi-loop circuit, you have to solve a system of equations. And you're not going to have to solve a system of equations on the test, because I don't do that on tests. But if you look back at old tests, and we'll do some in class, you'll see how I can make the multi-loop circuit slightly simpler mathematically. You have to apply the same rules, but you don't have to do all the algebra. Well, let's do this one. We're going to look. This is a multi-loop circuit. It's the simplest multi-loop you can have. I want to write 4 equations. I'm going to write an equation here for the left loop. I'm going to write an equation for the right loop. And I'm going to write an equation for the big loop. That's the big loop right here. See, there are 3 distinct loops in this circuit. So let's do the big loop first. Notice that I've already put the current directions. And sometimes on your test I'll give the current directions and sometimes not. But I just chose them here so we can all be on the same page. We'll do some where it's not given. But the current directions are not important. All right? It doesn't matter what you choose for the direction of the current. And I'll show you what I mean by that in just a bit. So let's do we'll do the big loop first. The big loop, I'm just going to choose to start somewhere. I'm going to start right here. Plus or minus, and I'm going to go in this direction. Plus or minus V1? Plus V1. Because I'm going from low potential to high potential. It's like a little slide that goes up. Here I'm going with the current. Notice the current comes here. Is that plus or minus IR1? Minus IR1. And be very careful, because notice that I have 3 different currents in this circuit. I have a current that runs from this junction all the way over to this junction. I have another current that runs from this junction down to this junction. And then I have a third current that occupies this third part over here. So in a multi-loop circuit, these are the most complicated you'll see. But in these multi-loop circuits, you'll have 3 distinct currents that run between the junctions. Anytime I come to a junction, my current will change to that junction rule business. Minus I1, R1, plus or minus V3? Minus V3. It's like that little girl going down the slide. And minus the toe. Minus the toe. There you go. That's a good way to remember that. If you go down the slide, it's minus a toe. You know, that was my mom's friend, actually. It was a child, my mom's friend. And we didn't have licenses or anything back then, right? There was no certificate you get from the state. So fortunately, the mom was okay with having a 9-toed daughter. Plus I3R3. Yeah, we run things in Mississippi just a little bit differently. Am I right? Where's Mississippi? Oh, right. Okay. Yeah, Sheldon, I'm sorry. It doesn't matter about the direction of the current. It only matters the direction that you're traveling. That's a good question. As soon as I get hung up on that. He asked, why is this negative and not positive? Because the current's going this way. But with batteries, the current is not important. With batteries, it's only the direction that you're traveling. So it'd be plus V3, or excuse me, negative V3, or plus V3 in this direction. It's an excellent question. Thank you for clarifying that. Let's do the left loop. All right, I'm going to pick a different direction. I'm going to go in this direction for the left loop, just for kicks. All right, I'm going to have plus I1 R1 minus V1. Is it going to be plus or minus I2 R2? Because I'm doing this loop right here. Plus or minus I2 R2. You remember the direction of the current is important. It's minus. Maggie? Nope, now we're doing the left loop. So here we did the big loop, the big outer loop, and now we're doing the left loop. Is that clear? I think I understand where you're confused. Let me say this and see if it fixes it. You have different currents at different parts of the circuit. So here, on the big loop, I had I1, where did I start for the big loop? I started right here. I had V, I had I1, R1. Over here I had V3, and here I have I3, R3. And then I come back to where I was. That closed the loop. Now I'm doing the left loop. I haven't finished it yet. But the left loop, I'm starting here. I have R1 through which I1 flows. So that's going to be I1, R1 because I'm opposing the current. Here I have negative V1. And then I have I2, R2. And then I need to do what? Plus or minus V2. Plus V2, right. William, you got a question? William, you have a question? No. Okay, so that's the left loop. Listen, I know this is kind of funky right now. Once you get these four little rules, the sign conventions, you okay?
I just look at them as secrets.
She sees not parallel. Don't do it in parallel. I don't even know what that would look like. All right, so a right loop. Let's do the right loop. Let's just start here and go in this direction. Remember, there's two directions. There's the direction of the current, and then there's the direction you travel. So we're going to go here, plus V3, because I'm going up the slide, plus or minus V2. Minus V2. Now think, don't answer right away, but what is going to be my next term? All right, what is my next term in this? Minus I2R, no, not minus, I'm sorry, plus I2R2. You're going against the current through the R2, through which the current is I2, because I2 operates in this middle branch. So it's plus I2R2. And then minus I3R3. That's all equal to 0. So you got your sign conventions, that trips students up. You got your currents, that trips students up too. Because you got to make sure that you get your right currents for each particular branch. But as you're working them, just be careful in how you're writing things. Make sure that you're neat about it, that you keep everything sort of organized. And be careful too with the direction that you're choosing. It doesn't matter the direction that you choose, but you have to be consistent with the direction that you choose for the current and the direction that you choose as you travel through the circuit. All right, we can also apply the junction rule. Those are 3 loop rules. In the junction rule, I would pick any junction. I'm going to choose this junction right here. I'm going to say the incoming currents are equal to the outgoing currents. Junction rule says I in equals I out. What currents are going into that junction? Okay, I2 is going into that junction. What else? I3. I1 is also going into the junction. See, because they're all have the arrows down here. They come around. I3 is going in there. I1 is going in there, and I2 is going in there. So I got all the currents are coming into this junction. So IN is I1 plus I2 plus I3. And the outgoing currents? There are none. Like, that doesn't make a sense, right? How can I have my 3 currents add up to equal 0? Well, you can have 2 reasons. Well, let me tell you the first reason. This doesn't happen very often. Sometimes you can have a circuit that's set up like this, and you have batteries that are, some are opposing other batteries, and they just don't produce any current, because the batteries are like, one's pushing in one direction, another's pushing in the other direction, and they just don't create any current. But remember what I said, that it doesn't matter the direction that you get for your current. Because when you solve for current, for I1, I2, or I3, some values might be negative. Some values might be negative. So for example, let's say that I solve my system of equations and I find that I1 is equal to negative 2 amps. I just get a negative number. And I don't really know why I got a negative number. Like, what does that mean physically to have a negative current? I'm going to tell you in a second. I2, let's say, is 4 amps. What would I3 be? In order for this equation to be correct, I3 would have what value? Negative 2. So I3 would equal negative 2. What that means, and it depends on your voltages, right? I just chose some numbers. But what that means is that I1 and I3, the directions are opposite what you wrote. So instead of I1 being, what was it, counterclockwise, instead of I1 being in this direction, I1 is actually in that direction. And I3 would be in that direction. That's why it doesn't matter what direction you choose for your currents. Because in the end, when you calculate them, it'll fix itself. If you chose the direction incorrectly, it'll come out negative. Okay? Does that seem complicated to you? Let's work through an example, because I think then it will not be as complicated. We have those four sign conventions, the loop rule, which we've seen already, and the junction rule. But those four sign conventions for the resistors and the battery. I'm going to make this one a little bit easier. And this would be more like what I'll have on the test, okay? I'm going to take out this resistor. I'm just going to imagine that that resistor does not exist. What that does is that gives me an equation that just has one variable, which means that you don't have to substitute one equation into another, which is kind of a pain. So good test question. Good example of a test question. Let's write some equations. You'll have some questions too where you just have to pick out the right equations, and probably next time, I don't think we'll get to it today, but next Friday we'll finish up this chapter and we'll do a few questions like that. Let's write some equations. First, we want to pick the direction for the current. I'm just going to pick some. All right, y'all choose the same ones that I choose, but you could conceivably choose different ones. But please choose the ones that it makes life a little easier. So we'll call this current I1. Let's call this current I2. And we'll call this current I3. I don't have any reason for picking those directions. I just picked them. Doesn't matter. I chose I1. Remember, I1 runs from here all the way over to here. I2 runs left to right. And then I3 runs in this loop. Now I'm going to write two equations for the loops. I want to do the top loop first. No reason really. I'm just going to do the top loop. Though as you get better at this, you'll see that sometimes there are equations that are better to write than other equations, just because they'll work out to be easier. So I'm going to write the top loop, and let's start right here. You go ahead and take a moment and write the equation traveling in this direction with the current. Write that equation for the top loop, and I'll give you about 30 seconds. I'll go from there. Alright, that's what we get for the top loop. Now, if you chose a different direction, you'd just get this, but with a negative in it. Or if you chose different current directions, you'd get a slightly different, some of your signs would be different. But as long as you follow those conventions, everything will work out the same in the end. I have plus 14, it's like going up the roller coaster. I'm going with the current, so I get negative IR1, and then, excuse me, negative IR, making sure that we know that it's I2. Just a second. And then I get plus 10 because I'm going up the incline. Yeah. Oh yeah, it should be I1. Thank you. All right. Yeah, that's a 1. Now let's write the bottom loop. And you know, let's just start right here, and we'll go in this direction. Plus 10 plus 2i3 equals to 0. Notice that if you wrote the equation for the big loop, I'm not going to because it's not really useful, but if I wrote the equation for the big loop, it would have 2 unknowns in it. Because the big loop, well, it'd be plus 14, minus 4i1, minus 2i3. So I'd have both i1 and i3. So on the test, you'll want to find loops that just have one resistor in them. Or look for those branches, like right here, where I don't have a resistor. It makes your life a lot easier algebra-wise. You can still get to the answer using the big loop, but it's just going to make it a little more difficult. Let's go ahead and solve these two. It's 24, negative 24. So this is I1 equals positive 6 amps. Isn't that right? 24, yeah. Positive 6 amps. And this one is I3 equals negative 5 amps. Oh no! I chose the direction for I3 incorrectly. That doesn't matter. We're going to keep our negative sign, but then at the end, we'll make note of it and say, oh, the direction of I3 is really in this direction. But now I also want to find I2, so we're going to apply our junction rule. Yeah, Brittany? Okay, let me break down the algebra a little bit more. So I have 14 plus 10 is 24, minus 4i1 equals 0. And so I have negative 4i1 equals negative 24. Divide both sides by negative 4, and I get positive 6 there. You know, sometimes I get my negatives wrong too, but a good way to check this is to take this and plug it back in up here. So that 14 minus 24 plus 10 equals 0. So the numbers that you'll be dealing with on the test will be whole numbers for the most part. And so you can do some of that math without too much effort. So just take that number and plug it in back into the equation. But writing your equations correctly will be very important. In fact, you'll have some questions that'll just be about the equations. And then here for the negative 5 amps, I would have 2i3 equals negative 10. I take this over to the other side, and I3 then is negative 5 amps. Is that clear? All right. I know there's a lot of you that struggle with your algebra, okay, but it's going to be particularly important for this test as we deal with these circuits in particular. All right. Practice, practice, practice will help. But if you need help otherwise, come see me. I'm willing to help you, and I'll be around next week. Oh, Thursday and Friday next week. Okay, now let's look at the junction. I'm just going to pick a junction. Doesn't really matter which one. IN, the currents going into this junction are I3 and I2. So I have I3 plus I2 equals to, the current going out is I1. So that's my application of the junction rule. Depending how you draw your currents here, it might be different. Or depending which junction you choose, it could be different. I mean, I chose the other junction. It would be I1 equals I3 plus I2. Almost done. I know I3 is negative 5 and I1 is 6. So I say negative 5 plus I2 equals I1, which is 6. Add 5 to both sides. I2 equals 11 amps. So how we would report the answer here is that I1, I2, and I3. I1 is 6 amps. Counterclockwise, or I might say to the left, referring to it going to this direction. Because it came out positive, that direction was correct. I2 was 11 amps. I would say I2 is to the right. And then I3, what would be the direction for I3? We drew it here to the right, but it would be what? To the left. To the left. Or you could, I'll do right, left. I think that's easier for us to. Or you might see elsewhere it would be, what would that be? Clockwise. So you don't make your sign adjustments until the very end. Notice here when I applied the junction rule, I kept this negative sign. Even though a negative current does have a meaning, but it just means that it's changed direction. But here our current doesn't. The meaning is important in how we do our calculations. Okay? Let's see. We're going to do some more. I want you to, you'll certainly have a question like this too. Let's try this. Which of the following equations for this circuit is correct? Now I've labeled the directions of the currents on the circuit. What you need to do is, well, let's see, this one's, A is not right. Right? This one is not a correct equation. So let me show you how I know that. I start right here because I see the 6-volt battery here, and I see that this should be a 6-volt battery. And already I'm sort of messed up, like maybe I'm supposed to be going in this direction, but I see the 8 ohm resistor coming right after. So this should be plus 6 minus 8I1. So already I can just get rid of that one, because it's not correct. So go through, one of these other three is a correct equation. I generally list the elements in order, so you can follow them. Like I can see right now that 6 minus 8I1, at least those first two parts are correct. I don't know about the rest of it. But the first two parts, as I travel through the circuit, are correct. All right. Let's stop at 2:30. So just 5 more seconds. Just guess if you don't know. Okay, good. B is right. A. That's good. Y'all getting this okay? Yeah? Let me show you. So let's step through each one. I've already shown you that A is not right. So we can show you that B is right. I have 6 minus 8I1, and then plus 2I2. I better be going against the current, and I am. I'm going against the current, so it's plus IR, and it's 2, and you got to get the right current, get the number right here. So if it said like I3, that would not be correct. And then you're going down the slide and, minus the total. Right, so down the slide is minus 12. And then coming here, going with the current, is minus 4I1. So this one looks as it should look. Let's look at our junction rule. Just pick a junction, it doesn't matter where, you only have two. The currents coming in is I3, and the currents going out are I1 and I2. So it should say I3 equals I1 and I2. That's not what it says. And then let's say here, I have 12 minus 2I2, starting here, positive 12, minus 2I2, we're correct so far, minus 8I1, that should be what? Plus 8I1. Check your signs and check your subscripts. So if this had 8I2, then that would be wrong as well. Minus 6, that's right. And this should be plus 4I1. So this should be a positive and this should be a positive. Okay? You'll have a question like that too. We'll see another one on the test. Similar to that on the test, but let's see. Let's do this one too. I like to do this. If the current I2 is 2.45 amps, what is the magnitude and the direction of I3? I2 equals 2.45, positive 2.45. What is the magnitude and the direction of I3? We can choose a loop where you can solve without much fanfare for I3. I'm going to bring this right back, okay? All right, let's go ahead and put in your answer. Many of you have the right answer, but some of you do not. All right, let's stop at 235. Very good. A is right. So what you want to do here is pick the right loop, because if you pick the wrong loop, it's going to be hard. Now, you can either choose the left or the right loop, right? I want to know the magnitude of I could choose the big loop too. Like I could take the big loop and try to solve for I3, but then my equation will have I1 and I3 in it. You could get to the answer that way, but if I want to know I3, the best way is to do this right loop, right? Because I already know this current, so it removes that unknown, and so I can write the loop for that. Let's just start right here and go in this direction. I have 12 minus 2I2 minus 3I3. That's equal to 0. I2 is 2.45, so that's 12 minus 4.9. That's 2 times 2.45. Minus 3I3. That's equal to 0. So let's see, that's 7.1 minus 3I3. Is that right? Yeah. And then I3 is equal to negative 7.1 divided by negative 3. What was the answer? 2.37. Notice that it comes out. Oh, did I do something wrong there? Looking for I. Yeah, I'm looking for I3. I notice it comes out positive, so it's labeled as down, so that will be the direction downward.
Why would you use I3 for that? For the three.
Oh, for the three students mess this up a lot, okay? So remember, she asked, why do we use I3 here? I3, the current here, runs from this junction all the way over to this junction. Your currents always change at the junction. You have an independent current here, an independent current, or not in it, but a different current here and here, and then likewise, we have a different current here. At the junctions are where your currents change, because you got other currents coming or going. That's the tricky part for students. They sometimes forget which current, or not careful, like even if they know it, they're just not being careful in how they label their currents or how they're approaching it. Loop rule is very useful because it allows you to, like I said, look at a big circuit, which you might see at some point, especially if you go to grad school, look at a big circuit and pick out a tiny portion of it, and you can apply the loop rule and find out a lot about what's going on in that circuit at that point. All right, let's see. Let's try this one. What is the magnitude of the current I1 in this circuit? If you pick the right loop, this thing becomes super easy. All right, many of you have the right answer, I think. Just ask your neighbor, just one or two of you. So ask your neighbor what they put. About 10 more seconds. Stop at 110. 110. Very good. Yeah, you want to do the big loop, right? And in fact, this looks a lot like a parallel circuit, right? Like one we've done where it just has a battery and then it has two parallel branches. But then I got this battery right here, and you're like, that should affect current in some way. But the loop rule would never like it. So you follow your loop rule, you go around, you do your loop however you like, and you get, plus 40, plus 20 I1. I1 has to have a magnitude of 2 amps. Let me write that out. So if I take my loop beginning here and going in this direction, I get plus 40. Coming up here, I get plus 20 I1. And that's equal to 0. So I1 equals negative 40 over 20, or negative 2 amps. Now I was just asking for the magnitude, but if I was asking for the direction, it wouldn't be to the right, it would be to the left. All right? Let's do this last one. All right, awesome. All right, let's wrap this up. Another 10 seconds. 10 seconds. Stop at 55. 55. Okay, very good. A is the right answer. Start here, minus 80I3 because I'm going with the current, minus 1I3. I'm going down the slide, so it's minus 20I2 because I'm going with the current, down the slide, so it's minus 40. All right? Not leaving, I need to talk to you for just a minute. I'm going to stop the recording.